Hello everyone, this is Ghayth and I'm excited to share with you our work today. Dynamic parallelism is a feature whereby it enables threads executing on the GPU to also be able to launch other grids of threads. And this is typically useful to implement computations with nested parallelism. However, in practice, using dynamic parallelism might cause many small grids to be launched, and that's not desirable and causes performance degradation due to the following reasons. Congestion, because devices can execute a limited amount of grids simultaneously. Hardware underutilizations, because if these grids are small, then there might not be enough threads launched to fully utilize the hardware. The solution is to launch fewer grids of larger sizes. Prior work had been done to address this, and we namely mention aggregation. Aggregation is an optimization whereby multiple child grids would be consolidated into a single aggregated grid, and then one parent thread does the launch instead. We take this example, we can see 4 parent threads. Each one of them would discover some dynamic work and does a launch. So they do launch 4 separate grids. We apply aggregation, and now instead of having each one of them does a dynamic launch, they consolidate their work in memory and one parent does one launch. Our contributions, we do thresholding as a compiler optimization, coarsening in the context of dynamic parallelism, and aggregation at multi-block granularity, whereby previous work did only consider warp, block, and grid granularity. And then we combine all of these optimizations into one compiler framework. Our first optimization is thresholding. Thresholding is an optimization whereby a dynamic launch is only done if the number of child threads exceeds a certain threshold. Otherwise, we execute the work sequentially in the parent thread. Take this example where we have 4 parent threads. Each one of them discovers some dynamic work, does the launch with variety of sizes, variety of work needed. We apply thresholding. Now, instead of having each one of the parent threads do a dynamic launch, only the ones with potentially high enough amount of work would do the launch. Otherwise, the work would be serialized and done in the parent. The second optimization is coarsening. Coarsening is an optimization whereby the work of multiple child blocks would be assigned into a single child block. We take this same example again, 4 parent threads, each one of them does a dynamic launch. We highlight the count of the child blocks executing here. We apply coarsening, and now we can see that the work of multiple child blocks is being assigned into one. The third optimization is multi-block granularity aggregation. It is an optimization whereby the child grids of multiple parent blocks would be consolidated into a single aggregated grid. In this particular example, we see 4 parent blocks. They would have parent threads. A variety of threads does a dynamic launch, and we end up with several grids launched dynamically. We apply aggregation. Now, instead of having each thread do a dynamic launch, they would consolidate their work in memory, and one of the threads does the launch. Here we highlight that we do this aggregation on a multi-block variety, and when we compare it with previous work, namely block granularity, with block granularity, each block would have at most one dynamic launch, whereby here we are launching fewer and larger grids, because here we are consolidating on the level of multiple blocks. And in this particular example, we are consolidating for 2 parent blocks. When we compare it to grid granularity, this would launch the child grids more eagerly, because in this case, we would not have to wait for all threads to consolidate their work. As soon as the 2 blocks finish consolidating their work, we do the dynamic launch, whereby with grid granularity, we would have to wait for all the parent threads to consolidate their work and then do the launch. To really speed up, we evaluate all the combinations for our optimizations for 7 benchmarks with 2 data sets each. We compare to a baseline that uses CUDA dynamic parallelism, CDP. Our first observation is that if we don't use CDP at all, then it is better than using it naively. Aggregation by itself improves the performance over CDP. Also, thresholding by itself improves the performance over CDP. If we apply thresholding and aggregation together, then it improves the performance even more, which means that one optimization does not obviate the other, even though aggregation and thresholding does target the same sort of inefficiency. Our fifth observation is that coarsening by itself does not really improve the performance. And then if we also apply coarsening with the other optimizations, then it also improves the performance. It is about 1.22 times faster than CDP plus T plus A. To sum this up, we present a compiler framework for optimizing dynamic parallelism with applications that uses nested parallelism. The framework includes 3 key optimizations: thresholding, coarsening, and aggregation. Our framework does substantially improves the performance with applications with nested parallelism. It is over 43 times faster than CDP, 8.7 times faster than not using CDP at all, and 3.6 times faster than aggregation work, namely CLAP. Thank you. Please let me know if you have any questions.